Thank you. So I'm Nissy Abraham. I am a data engineer and a first-year PhD student. I'm looking into maternal health as part of my PhD, and I've started working. I'm a first-year PhD student, basically. So, Sai.
I'm Sai Varik. I'm also a data engineer at University of Birmingham and currently in the first year of my PhD program. Thank you, Kevin. Thank you. Good afternoon, everyone, and thank you for having us today. Today, we are going to walk you through how we model two different clinical data systems, Vaginet for maternity and PICS for acute care raw data, coming from various different NHS sites across the West Midlands, and how we turn them into single standardized research-ready format. Next slide, please. So we had PICS and Vaginet raw data sitting inside the secure data environment, which was unusable for research on their own. From there, we had to lay the groundwork of building inside a secure, trusted environment and designing a model that could handle this raw data. Then came the real work of engineering. Both of these data sources at scale across hospital sites into one common research-ready model. And the payoff is what you are about to see. The real studies delivered end-to-end, and we are taking this next. Let's start with the environment where data sits inside. The West Midlands Secure Data Environment is a trusted platform that brings together healthcare data from multiple NHS sites and care settings, with strong data governance aligned with HDR UK 5 SAFE's framework. But here is the challenge we kept running into. Every research project meant building its dataset from scratch, which involved manual data extraction, manual quality checks, and formatting for every single study. This slows down the research, it delays grant opportunity and collaborations. The solution for this is the software developed here at the University of Birmingham, named Dexter. This software generates research-ready data rapidly by cutting down the time to prepare the data from months to hours. The Dexter was first developed for primary care data, and it is well established there. What we are doing now is extending the same proven approach into secondary care and maternity care settings. This is Dexter in one picture. I know it looks quite technical, but let me simplify what Dexter actually does with a real-world example. Say, you want to know how many patients with type 2 diabetes were given SGLT2 inhibitors versus DPP4 inhibitors. Normally, this takes a week or months of manual extraction before even you start analyzing anything. But with Dexter, you come up with your study design, fill in the forms on the Dexter user interface, click a button, and within hours, you have your data ready for research. Additionally, Dexter also has analytics engine, which helps to analyze the extracted data. Please. Here are some of the key features of the Dexter software. It works across different environments without any data ever leaving the secure home. It adapts to many different database structures. It does not require any heavy infrastructure. It can scale to millions of patient records. It also comes up with a built-in phenotype library for common study designs. And critically, it's built to be transparent, reproducible, and not a black box. Now I will hand over to Nissy, who will walk you through the maternity data modeling.
Yeah. So I'm going to take you through the process of modeling maternity data resources into a research-ready data format for rapid research. So why maternity now? So maternal mortality in the UK has been is rising, and it's more when compared to 2 decades ago. And it's not evenly spread. It depends on the socio-economic status, the ethnicity of the women, and so on. So there is inequalities and differences in the way that women receive care in the UK. And there are repeated inquiries that points out the same thing. So there's the Ockenden review, the Kirkup review, and most recently the Amos report, which all points to issues that are in the maternal services in the UK at this point. And why should we use the secondary care EHR for research to solve these issues? It's because the EHR holds a lot of nuanced and critical information during labor and delivery, which could be lost in translation when a data set like a pregnancy register or MSDS and the likes are built, because they standardize data into the standard format and it loses a lot of critical nuanced information that's there in the EHR itself. And there are a lot of different systems, maternity EHRs. In the UK, Badgernet is widely used, Epic is being adopted, so on, in a lot of different trusts and so on. So the objective of this project that we have worked on right now is to build a solution that is common for different EHR systems, different data sets and different trusts, that is scalable and also reusable. So it can be used across the region and nationally as well. The data sets that the maternity Badgernet data set that we have in West Midlands Secure Data Environment comes from 3 different trusts: Sandwell and West Birmingham, University Hospital Birmingham, and SAT, which is Shrewsbury and Telford Hospital Trust. 3 maternity services have contributed their Badgernet maternity data into the we have got it in the West Midlands Secure Data Environment. Badgernet itself is an application that's form based, so the information about the pregnant women and the different antenatal bookings and so on are recorded in a form based system, and that stores this information in over 200 tables, and it stores in a XML format, which is converted into over 200 plus tables as a reporting server. And the reporting server data is what we have got for basically research. As you would know, there's no standard coding systems within this form-based system, which means that all the information is stored in an unstructured data format, and there's no clear data dictionary available to understand where this different form information is being stored in the data model that is in the Badgernet. So, for example, VTE during stay is a column that we came across that does not actually mean that they had VTE during stay, but means that they had a risk assessment for VTE during stay and so on. So there is a lot of information does not directly translate to when we just look into the data. And we decided to map it and create a common data model to do maternity research with this data. When we started off, we tried to use existing common data models, say the likes of OMOP and so on. We did feel a little bit of technical difficulties trying to do it directly, meaning like I said, there's more than 200 tables in Badgernet. The idea is to map those concepts into the common model, OMOP or other common data models, is to understand every single table and individually map the concepts to the concepts in the common data model, which needed technical expertise in the source data itself, and also it takes time and also computationally expensive to do it in a TRE setting. And most common data model are general purpose designed, so a lot of nuanced information about pregnancy could be lost in the concept-wise translation into the common data model. So we decided to build a bespoke common data model. We would probably try to map into OMOP as well, but at this point, we felt it's easier it was straightforward for us to build a bespoke common data model that actually gets all the information that's in the Badgernet without losing anything, and it's also efficient to use. And every time we try to convert a data into the common data model, it would need only minimal manual intervention from us. So that's why we decided to go with a common data model on its own, which could work with Dexter and helps us do rapid research. So the solution, the common data model that we have developed is based on building generic concepts which can translate the data from source into the common data model without standardizing or forcing standardization at earlier points. So everything comes into the common data model as well with a fallback table which captures anything that cannot be classified as a defined concept. I'll take you through the common data model itself in the next slide. And it can handle different coding standard and non-standard coding systems. It should, I say, and it's source agnostic. The solution that we have built is to work with Parquet version. Parquet is columnar data store, which is really good for analytical research. So when compared to traditional databases, Parquet format increases the efficiency, the speed that we can work with these data. So we have built it around the Parquet data store, which makes any data source to be easy to be converted into Parquet format, and the pipeline that we have built to convert into common data model should work without manual intervention, and it is reusable for different trusts and different applications. So this is the pipeline that we have built for converting the source data. Here it is BadgerNet reporting service maternity data. It could be any other source data in the future. Once it's converted into Parquet format, the first step is to define the pregnancy cohort itself. So identify the start and end of pregnancy with the LMP and EDD information in the EHR, along with the different appointment dates and the gestational age, which will help us identify different time points within the pregnancy, and also captures labor and delivery within that timeline. So define the start and end of the maximum follow-up, which is 6 weeks after the pregnancy within these EHR systems. So we have once we define the pregnancy, we identify the patient, the mother who's which is mother patient who's associated with the pregnancy itself, and link it to the baby patients. So the first 3 tables, pregnancy, patient, and linkage, are the tables that captures these information that's defined by the pregnancy cohort. And then we have other 4 tables, which is measurement, medical, therapy, and additional. Measurement is captures all the measurements that the woman has had during booking any appointments or during labor and delivery, any number and value and a unit that's measured for the mother patient or as well as the baby patient. And all the medical events of the mother and the baby, and all the prescription drugs given, as well as we do not have it in prescription as a module within BadgerNet, but all the prescriptions could be added to the therapy table. And additional is a fallback table, which captures any concept, any information that does not fall into the 3 categories above. So this data model brings together the entire EHR data without losing any nuanced information into the common data model, which can be directly this common data model is what we are trying to convert these source BadgerNet data into. So the Parquet version is profiled, and the profiler is a tool, a Python-based tool, which profiles the source data, identifies what data should go into what concept, potentially concepts, and it maps to the target table. Once the mapping is done, it's converted into an CSV format. That's the config which is used by the next step, which is the ETL pipeline, to read this data from the source Parquet version and convert it into the research-ready output model that we see here. So the data that we have processed up until now within the West Midlands secure data environment, like I mentioned, has 3 different trust data. So there's approximately 170,000 pregnancies from Samuel and West Birmingham, 108,000 pregnancies from UHB, and approximately 20,000 pregnancies from Shrewsbury and Telford with NHS Trust, and a total of 288,000 pregnancies after deduplication and removing data that has issues and incomplete information and so on. 288,000 pregnancies what we have in the West Midlands secure data environment ready for research. And among them, we have 202,000 pregnancies, which is approximately 70% of the data is complete, which means that it has a date of delivery and the baby information. Through the complete pregnancy cycle is recorded for these women and different other categories of pregnancies within the data set. Once we have converted the entire data into the common data model, we do perform quality checks to confirm that the data is intact, it's complete, which means that the source data is what we have in the common data model. We have not lost any data. And we also run a set of validation rules that checks if the data follows all the rules that we would require in this data model to be ready for research. And before we release it to the researchers, we confirm that the quality checks is all passed. So that's how we convert. The quality checks and validation is also applicable for the acute care as well. It's the common step that we do once the data is in a common data model before it's fed into Dexter for extraction for research. So over to you, Sai, to take us through the acute care data processing.
So the aim follows the same underlying principle: to leverage the availability of PICS data by building a model and scaling up the research. The Prescribing Information and Communication System, which is commonly known as PICS, is locally developed electronic prescribing and patient record system at UHB. It is used across inpatient, accident and emergency, and outpatient care. To give you a sense of scale, we had around 100 of source tables, data going back to 2010, and close to 2 billion of record across 4 different hospital trusts. The acute care data model looks similar to one we developed for maternity care, with one key change. In place of pregnancy forming the backbone of the model, we have introduced the concept of admissions, which serves as the entry point of the patient journey. Also, the overall idea behind data pipelining is similar for both acute care and maternity care. But of course, the data transformation and mapping differs. On this slide, I will talk about the admissions breakdown. We started with 37 million source records, which were coming from outpatient, inpatient, and accident and emergency care. To begin with, we just focused on processing the inpatient admission, which is around 8.3 million. From there, we mapped the episodic view of this record into their respective admissions. And after deduplication of these admissions, we were left with around 6.7 million inpatient admission across 4 different hospital trusts. Now, since PICS was installed at different sites at different time points, we applied each site's installation date as the starting point. And once we account for that, we were left with around 2.5 million admissions available for research. So, what does all this work actually unlocks? First, a standardized foundation for scalable and reproducible research. Second, it enables the development and validation of clinical prediction models, risk stratification tools, and population health analytics. Third, it supports epidemiological studies, cohort studies, service evaluations, and analysis of patient pathways. Fourth, it significantly speeds up identifying eligible patients for clinical trials. And honestly, this is not the full list of data, what this data can bring to the research. It can do many more things. We really wanted to put this software to test with this real world data. So we organized a one-day datathon. We had a mix of people with different backgrounds who took part in this datathon: clinicians, researchers, analysts, and data scientists. We organized 4 specialist teams on the day for study design, phenotyping, data extraction, and analysis. The goal was simple. By the end of the day, we should complete 4 research studies, 2 PICS and 2 using VaginNet data. And we did it. Now we are looking forward for more collaborations and running many more datathons like this. Next slide, please. Our first study was a pharmacoepidemiology study. Using the UHB inpatient cohort, we ran a propensity score matched retrospective cohort study comparing SGLT2 inhibitors against DPP4 inhibitors. as first inpatient diabetic prescriptions. What we saw was that overall, SGLT2 inhibitors demonstrated a favorable safety profile with lower risk of acute glycemic and sodium-related events, shorter hospitalization, and a reduced risk of short-term mortality. Our second example is a prediction model for post-surgical complications. The exposure covered a wide range of surgery types, neurosurgery, endocrine, breast surgery, and several other surgeries. The outcome was composite outcome covering sepsis, cardiac complications, respiratory complications, and surgical site infections. The data was split into development and validation purpose. The model was developed using the data from Queen Elizabeth Hospital and validated using the data from Heartlands, Good Hope, and Solihull hospitals. Overall, the model achieved a performance of 0.78. Over to Nissy.
During the same data event, we did 2 maternity studies using the maternity data in West Midlands security environment. So the first one was to find how interpreter usage in their antenatal booking appointment affects pregnancy outcomes. So we compared women who needed all the women needed interpreter services within the cohort, and we compared the women who had an interpreter in their booking appointment to women who didn't have an interpreter, a formal interpreter during their antenatal booking appointment. And we found that the usage of formal interpreter in their booking appointment did improve some pregnancy outcomes, and it also improved engagement and experience the women had during labor. So the outcome is that formal interpretation does change quality of care that the women receive during their pregnancy and labor and delivery. The other study that we did was to find the association between gestational diabetes during gestational diabetes and adverse outcomes. So we did analysis to find out if preterm birth, like how gestational diabetes affects preterm birth in women within this cohort, within the cohort. So we had a cohort of women with 16,000 women had gestational diabetes, and compared them with women who did not have gestational diabetes. And the study suggests that the preterm birth in the GDM cohort is predominantly iatrogenic and not spontaneous. The distinction is that GDM should be included as a risk factor for national preterm birth as well. And some reflections from this project. We can achieve scalability through automation. So we have automated a lot of processes that we do. So we convert a lot of the data into Parquet format, which helps us automate a lot of steps that we do to convert the data from source to the common data model. And hashing could be a solution. So when it is large string, working with the querying it and saving it is it is intensive, and hashing could be a solution. That's what we have used when we are working with the non-standard codes within the maternity data set. And Parquet as a solution, I've already explained it is a good solution when we are working with large analytical data sets because it takes minimal memory storage, but also is extremely efficient and fast when we try to query the data. And we have built the solution with reproducibility as at its core. So the data could be reproduced with the same pipeline into the common data model, and Dexter as a solution is also designed in a way that it reproduces the same data set every time. If you work with the same, if you give the same definition, it is going to generate the same data set every time. So that helps with reproducibility. So the ongoing work in this project for UHP maternity, we are linking it to PICS to get the potential prescriptions, CTG data during labor, and any USS data that's available. We're trying to map it and onboard newer trusts. Acute care, again, we are trying to get data from other sources, and we are trying to also integrate inpatient, A&E, and outpatient data. This is to capture the entire pregnancy and the hospital journey of a patient. And the future work we are hoping to do soon is in the maternity space. We are trying to get a natural language processing to to convert this non-standard coding into any standard coding terminology. So it is easy to work with and reduces the effort needed to build phenotypes on top of it. And when it comes to PICS, we want to extend the DEXA solution to other EHR. So we are hoping to onboard a Cerner site to the same common data model. So that's all. Thank you everybody for listening to us. Especially we would like to acknowledge Professor Simon Wall, Stephen Perks, and the West Midlands Secure Data Environment technical team. They helped us with the environment to work with and bringing the data to the environment, pseudonymizing it, and all the other needed works that needs to go in before this data can be made available for research. And all the clinicians that we have worked with, so especially the maternity research group that comes together, and the acute care team that comes together helps us building phenotypes, coming up with ideas and how this can be made efficient and research ready. We have got a lot of inputs from clinicians and PPA members. We would like to thank everybody who had contributed during the development of this project. And if you'd like to collaborate with us, with the team and West Midlands Secure Data Environment, please reach out to Laura. The email address is here. Thank you everybody for listening.